problem number 4. In this problem, we've been given a sheet of tin, a square sheet of tin. So I'm going to start with that. This time the picture, instead of not moving the problem, I'm going to start by drawing this imaginary square of tin, like tin foil. And the sides measure 12 inches. Each side is going to have a certain amount cut out. Now, I'm going to draw this for you. We didn't really do anything like this in class, but I want you to imagine that if I took X as a piece, a square piece to cut out, I'm going to subtract that out by cutting it out. It's an X by X corner cut out from each side. And I should actually say each corner. If I cut that out all the way around, I can now make a box. And so I want you to see that I've made like a tabbed piece of paper or tin. That red stuff is gone. And I'll take each of those tabs that I've created and fold it up. And that'll create a nice little box. We're not going to worry about how to connect the edges to make the box watertight or anything, but this is one way we can make a box. The top of the box is open. So how large of a square is cut out so that the volume will be as large as possible? So there's our maximizing equation. Volume is going to be as large as possible. And we have to figure out how much of an X value square to cut out. So should get a volume equation here. Volume is, if we had that box with the sides folded up, now we imagine this box, and as we folded up those sides, we really have a height of X for that box. That's going to be coming from folding up the cutout red segment. So we have our regular volume equation is it's length times width times height. And we're just talking that the height of the box is X tall. The width of the box can be found by looking back at the original picture. And it looks like the width of the box is missing two pieces, missing those two little red X segments. The original length the original piece of tin was 12 inches. So it looks like I can call the width of the box the original 12 from the square of tin foil, and then subtracting out two X values, or two little X segments that I cut out. The length of the box, which would be over here on my picture, can be seen from above on the unfolded piece. And it looks like, because this is a square piece of tin, the length is also, it was 12 inches, and we cut out two X segments. So let me rearrange this a little bit. I'm going to move this X up into the front. The height times the width times the length. And because I've done this problem this way, we don't have a secondary variable. We're already in terms of just X. Now, like our original problem, we don't want to take a derivative of this product. We instead should rewrite the volume equation by distributing out the terms. You see that the two sets of parentheses is going to form a trinomial. Minus 48x plus 4x squared. Nope, not with the 2 in the front, but with a x in the front. So I just now can distribute through, probably because we like it, rearrange it to standard form. And by doing this, I've made a nice, easy polynomial to take a derivative of. So our derivative is 12x squared minus 96x plus 144. And when I set that derivative equal to 0, it looks like we have a factor of 12 in there. 96 divided by 12. I don't know what that is. 8? I think that's 8 minus 8x. And 144 divided by 12 is 12. I'm liking this because that is a factorable quadratic. And so I have x minus 6 and x minus 2. And then I've got two critical values, x equals 6 and x equals 2. So we're going to have to test two critical values. Now, if we want to talk about different ways to test the critical values so that we can see if they're maxes and mins, we could do that sign chart with the first derivative test. Or, because we have a polynomial, we could go ahead and do the second derivative test. I'm going to do that this time, giving you multiple ways to test these values. Going back up to our derivative, our first derivative located above. If we take the second derivative there, we've got 24x minus 96. Really easy second derivative. And so by using the second derivative test, what we're going to do is we're going to evaluate for concavity. So taking the second derivative and plugging in our critical value of 6, we've got 24 times 6 minus 96. Right off the top of my head, don't know that number because I hate multiplying. If this was not a calculator portion, I do suggest you go and do some little math up here instead of doing crazy estimating in your head. So I've got 144 minus 96, and really I don't even care about that true value of the second derivative. What I care about is it's greater than 0, which means concave up. And so at x equal to 6, we actually have a minimum. That's not what I wanted. That's not the critical value that I want. Let's check the other critical value. We're going to test the v double prime of 2 this time. And here we get 48 minus 96, which is less than 0, concave down, which is going to give us x equals 2 is going to yield a maximum for the volume. I feel like that's an example where the second derivative test is definitely worthwhile compared to a sign chart. Endpoints, I can think about what I can cut out as an endpoint. I could cut out nothing. That would give me no box. Or I could cut out everything, but if I cut that everything out, it wouldn't be the 12 inches I would cut out. Instead, it would be, I'd cut 6 by 6 out. That's going to yield no box either. And actually, that came up as one of our other critical values. So an endpoint was a critical value here. And both of them are going to yield minimums, which really makes sense. No volume is going to be the minimum of our equation here. So we've done our analysis, and now we just need to answer the question. So let's scroll back up. How large of a square is cut out so that the volume will be as large as possible? That means we don't care about the volume. If this was rephrased and said, what is the maximum volume, we'd actually have to plug our critical value of 2 back into V to get the volume as well as the dimensions of the square. But if we cut out x equals 2 inches as a square from each corner, we would have a maximum volume. And there you go. Nope. There you go. Not that. All right. Thank you very much. Probably done by now in class.